You could close the door, that'd be great.
All right, so our speaker today is my neighbor across the hall from me. Yes? So it's really great when I have to ask him something. Hey, you want to speak in science seminar? I just shout across the hall. Last week when it was his turn, this week he said, you're up next week. Okay, I got it. He goes back. So great communications there straight across the hall. I've never lived with the chemistry people. They put me in first office was over here with the engineers, right? And then they moved me to the math people. And my own colleagues don't want to live next to me. I'm not quite sure why, but it's really been nice to live with the math people. Hear all the good things that they do. Not only is Dr. Krause a math guy here, he is the chair of our math department. And I get the pleasure of hearing these guys meet in their math meetings in Dr. Krause's office. And they have to be the nicest people ever. Our chemistry meetings, they're always fighting and bickering and yelling at each other. And math people are so cooperative. They just go through this logical set. Well, if this, then that. And it's just, it's like, wow. I wish I could be a math person. Today, one other thing you should know. Corey Krause is not just a faculty here at LeTourneau. He was also a student here at LeTourneau. He got his Bachelor's of Science degree here from LeTourneau. And then he went on to get a Master's from Stephen F. Austin. And what do you think? Math, yes. And then he got his PhD in what do you think? Math from the University of, was it not math?
No, it wasn't.
Okay. All right.
Yeah.
So, today he is going to talk to us about exciting things in infinite dimensional vector spaces. Let's give a warm welcome.
Okay, well, I'm very glad to be here and to talk to you about this. I do plan to get to infinite dimensional vector spaces at some point, but this is also just going to be a general kind of talk about infinity in mathematics, kind of the history of infinity and how it's been used in mathematics, and I hope that you find it, appropriate for a general audience and that all of you can get something out of it. I'll try to get to the more abstract theoretical stuff later. So just some things about infinity generally. Infinity has for a very, very long time captivated a lot of different people from a lot of different disciplines, right? Not just mathematicians and scientists, but also poets and artists and theologians. We'll talk about the infinite and infinity. In some ways, it's almost more appropriate to talk about infinity from an artistic point of view. Infinity, when we think about infinity, it's kind of like that which we can't quite understand, that which we can't quite reach, the thing that we're approaching but we never quite get to. So you do see infinity show up in all sorts of artistic endeavors. So, for example, how many of you recognize this person? Anybody know who this is?
Escher.
Escher, yes, this is M.C. Escher. He's an artist who loved to create things that suggest the infinite. Right? And he was not a mathematician himself, but it turns out much of his work involves a lot of mathematics. So he was a visual artist. I don't know how many of you have heard of Jorge Luis Borges. He's one of my favorite authors in general, and definitely my favorite short story author. He has a lot of short stories where he kind of considers what it would be like to experience the infinite. He has this really famous one about being inside a library where every possible book exists. Right? It's called the Library of Babel. He has another story called The Immortals where he imagines what would it really be like to live forever. He has another story called The Aleph where he imagines what would it be like to see all places simultaneously. Right? And they have a very kind of mysterious, kind of mystical flair to them. They're really fun stories. If you haven't read any Borges, I suggest that you check him out. He's pretty fun. How many of you know what that is? Anybody know what that is? Sam?
Oh, no, don't ask me.
Okay. Sam knows what it is, but he might not remember the name of it. It's called the Shepherd scale or the Shepherd tone. It's something that it increasingly ascends, but after it ascends a certain amount, some of the notes go back down. So it gives the impression that it's a continually increasing scale that never actually stops going up. You can listen to it. I don't have an audio file, but you could listen to it sometime. And these are really, really cool. This guy, his name is Anthony James, and he creates these sculptures that use one-way mirrors and lights that you can peer into them, and they sort of infinitely reflect the lights in one another. Look up some videos of those things. Those are really amazing. I want to go see them. Last time I checked, there's some of these at Crystal Bridges. I need to go in Arkansas. I need to go look at them. Maybe we could buy one whenever we get a math building. You guys can keep the spirit of ingenuity. I'm going to put one of those outside. It's like a new math building. We've got a math building. So, look, so we've got visual arts, we've got sculpture, we've got music, we've got fiction. Infinity is something that captivates us. Even from a very young age, we all are captivated by the idea of infinity, I think. Sometimes I grade in Panera Bread on Saturdays, and sometimes I overhear interesting conversations that other people are having. Just a few weeks ago, I was overhearing a conversation between two siblings, and they were doing that game that probably many of you played when you were young with your siblings. Who can name the largest number? So 1, 2, 3, 100, that's a pretty big jump. 1,000, 1,000,000. Well, it doesn't take very long before somebody says, infinity. Infinity. Well, what are you going to do with that? Infinity plus 1. Okay, well then the dad jumped in. He said, no, son. Infinity plus 1 is still just infinity. And I wanted to, say, well, in my expert opinion as a mathematician, I'll say some things about this. No, actually, this was very cool because after about 5 minutes, right, nothing was said for about 5 minutes. That young boy, he must be like 8 years old, 9 years old. He was thinking about it. And then he asked his dad, how can you add 1 to infinity if you can never get to infinity to add 1 to it? Oh, that's a wonderful question. That's a wonderful question. Let me train him. Well, what he was getting at there is actually to say the distinction between what's called potential infinity and actual infinity, or completed infinity. This is a distinction which goes really far back in history of thought, okay? And it started where a lot of different ideas started with the Greeks. So let's begin to talk about infinity in mathematics, talking about the Greeks. Here's Aristotle, pretty influential guy. Here's some quotes from Aristotle's Physics. Right? So he says that the science of nature is concerned with spatial magnitudes of motion and time, and each of these, at least, is necessarily infinite or finite. Hence, it is incumbent upon a person who specializes in physics, right, to discuss the infinite and to inquire whether there is such a thing or not, and if there is, what it is. Okay, well, that's okay. There's his justification for why he's studying infinity in his physics book. He comments that only the Pythagoreans place the infinite among the objects of the sense. They do not regard number as separable from these. I really wish I had time to explain what he's talking about there, but if I can't, I don't have time. So if you want to know what he's talking about there, take history of math, and we'll talk about it. He says, infinity turns out to be the opposite of what people say it is. It is not that which has nothing beyond itself that is infinite, but that which always has something beyond itself. For the fact that the process of dividing never comes to an end ensures that this activity exists potentially, but not that the infinite exists actually. So you see those words, potentially and actually there. And from this point forward, there is a common distinction between the potentially infinite and the actual infinite. You can imagine a process that continues forever, but you can't imagine that process actually taking, the infinite number of steps actually being completed so that you could then add 1 to infinity after you've counted up to infinity. So this was Aristotle's opinion, and you know that Aristotle is a pretty influential guy. His view was not the only view around at the time, but it was certainly the view that won out. Aristotle believed that potential infinity is a type of infinity that is appropriate to talk about and to study from a mathematical perspective or other perspectives, but not the actual infinite. The actual infinite is not something that we can talk about as finite human beings. Okay, so that's the way it goes for a very long time. Aristotle's pretty influential. It stays this way for a pretty long time. Things start getting a little bit weird when calculus comes up. So jump ahead, quite a ways. So let me talk a little bit about the origins of the calculus. Now, that's anybody recognize that person? It's not Newton. It's not Leibniz. That's a picture of. This is Galileo. Galileo. You don't often hear about Galileo in connection to calculus. You hear about Newton. You hear about Leibniz. You don't hear so much about Galileo. But Galileo is a very important precursor to the calculus. He actually spent a lot of time thinking about infinity, and both things infinitely large and infinitely small, and encouraging his students, very important students, Cavalieri and Torricelli were both his students, to investigate things that really are prefiguring the calculus. So he's working 100 years before Newton and Leibniz, but he's already developing a lot of those techniques. He said in a letter, infinities and indivisibles transcend our finite understanding, the former on account of their magnitude, the latter because of their smallness. Imagine what they are when combined. So although he did have a kind of mystical view and it's paradoxical, some people like to avoid paradoxes, some people like to embrace them. Galileo was one of those people that kind of liked to embrace paradoxes. So he, although he thought they were beyond our understanding, wasn't afraid to actually try to use them in his math. It was pretty controversial at the time. The powers that existed at the time were pretty strict about a lot of things, even mathematics. And so there was, very much Euclidean geometry is the right way to do mathematics. You're not allowed to talk about the line as consisting of individual points. You're not allowed to talk about indivisibles or things infinitely large or infinitely small. The perspective of Aristotle was kind of the de facto way it had to be done. And I don't know if you know this, but on the list of heresies that the church that indicted Galileo with was not just his heliocentrism. You hear a lot about that. Galileo believing that the sun is the center of the solar system, not the earth, and how he got in trouble for those kinds of things. But if you look at the list, on the list is also all this stuff about indivisibles and infinitesimals and using infinitesimals. Did you know that? Okay, so that was you could add that to his list of heresies. There's a book about this, if you're curious about it, by Amir Alexander called Infinitesimal: How a Dangerous Mathematical Theory Shaped the Modern World. Okay, so while Galileo wasn't afraid to use completed infinities or things that are infinitely small, it wasn't really well accepted at the time. Galileo really wasn't able to justify his techniques, but neither were Newton and Leibniz. Okay. The intellectual atmosphere in England and in Germany was maybe not quite the same as it was in Italy 100 years later. And they were able to talk about infinitesimals and develop the calculus. But even they did not really have a full explanation for why the things that they did worked. They would have certain quantities that they treated like zero, but they weren't actually zero. Sometimes they were zero when they wanted them to be zero, and sometimes they weren't zero when they didn't want them to be zero. But they really weren't very rigorous. They knew that what they were doing they couldn't prove in the way that you could prove things about Euclidean geometry. Okay, so this was kind of just this, people just kind of accepted this. Why did calculus stick around then if nobody could do anything with, nobody could prove anything about it? Well, of course, because it was useful, right? It was very, very useful to everyone. It solved a lot of problems, but people didn't know how to really rigorously justify a lot of the things that they were doing. Not until this guy, Weierstrass. So he's a mathematician. This is actually in the 1800s, so you got to jump forward another, 200 years or so. And Weierstrass, he kind of saw everything that was going on in mathematics at the time. So for a very long time, people really weren't trying to prove things in calculus, or if they were trying to prove things in calculus, they were doing it from a geometric perspective, like Euclid would have done, or maybe they were using infinite series, but things were getting very messy. In fact, things were getting messier and messier as people tried to tackle harder problems in physics, from problems from electrostatics, electrodynamics, from the diffusion of heat. Things were getting more and more complicated. Right? Eventually, mathematicians started proving theorems that contradicted one another. I don't know if you know that much about proving theorems, but the theorems that you prove are not supposed to contradict one another. That's not supposed to happen. So for instance, just one example, there are actually several examples, but one example was that Cauchy proved that if you had a sum of continuous functions, then it had to converge to a continuous function. That turned out not to be right. Another example that is that Ampere, same Ampere's law, if you've heard of Ampere's law, supposedly proved that a continuous function could only be non-differentiable at a set of isolated points. Okay. That also turned out to be very wrong. Weierstrass showed that there was this function. This is the first example of a mathematical fractal. So this is a continuous function, right? It means you can draw it without picking up your pencil. Not really. You probably can't draw this without picking up your pencil. There's no holes in the graph. It is a continuous function, but everywhere you look, there's a corner. Every single place you look, there's a corner. You zoom in, another corner. Zoom in, there's another corner. No matter where you look, there's more corners. Right? It's actually the first example of a mathematical fractal. So you'll look at his definition here, and this is actually a type of Fourier series, and that's a big part of what is messing everything up. Fourier series turn out to be really powerful tools, and they throw kind of a wrench into everything. And mathematicians do not understand Fourier series very well. So Weierstrass created some problems, like this function, but he also solved a lot of problems. He actually was really the single person who, I think, most is responsible for the modern definitions of a limit, right? So the concept of limit took a long time to come about. Now we think of calculus as completely based on limits, not on infinitely small quantities or infinitely large quantities. But so a lot of those had, their precursors in Cauchy and others, but Weierstrass is the person who came up with the definition that you see here. I've written it in symbolic logic. But you may, if you've had Calculus 1, had to struggle a little bit with epsilons and deltas. If you take real analysis, you have to, that's probably half the course. So this is the definition of what it means for the limit of a function as it approaches a to be equal to L. So this is a very precise definition that Weierstrass came up with. And one thing you'll notice about it is I don't see any infinities anywhere. So I think my personal opinion is that whenever you see this symbol in a calculus textbook, it's a fake infinity. Personally, I think it's a fake infinity. Right? Because if you look at the definitions of all of these things that involve that symbol, you look at Weierstrass's definitions, they all involve only finite quantities, and they're only ever talking about potential infinity. So in some ways what Weierstrass did was that he got rid of a lot of the paradoxes that were in calculus by being more careful with his definitions, that's for sure, but also in a certain way he kind of eliminated the necessity to reason with infinitely small quantities or infinitely large quantities, and kind of put things back in terms of potential infinity rather than completed infinity. Okay, so I think that's a fake infinity. So what's going to happen? Is this the end of the story? No, it's not the end of the story. It might have been the end of the story, except for another person who now comes into the picture. A breakthrough happens with this guy right here. This is a very important mathematician named Georg Cantor, and he is probably the most important person for reintroducing completed infinities back into mathematics, to actually reason about completed infinite sets. Cantor's an interesting person because he was very religious, and he had a lot of religious motivations for actually doing this. Now, he didn't start by, okay, I want to investigate infinity because I want to know more about God. It didn't start actually with that. Not everybody always realizes this, but Cantor actually began studying what everybody was studying at the time, Fourier series, right? That was the big thing. That was the big thing everybody wanted to understand was Fourier series. So he was in particular considering, okay, when is the convergence of a Fourier series unique? Right? On what types of domains? Okay, and he was able to prove that that Fourier series of a function is unique if the domain that you're working with is what he called a perfect set. A perfect set is a closed set without isolated points. Okay, real analysis is a closed set without isolated points. That's a perfect set. Bonus question. So it's a closed set without isolated points, and he proved that Fourier series would be unique if they're defined on such, functions would be unique if they're defined on such types of domains. And it led him to ask, well, okay, what types of closed sets contain perfect sets? Right? Or what types of sets contain perfect sets? That ends up being a really deep question, and led him into just thinking a lot more about infinity. And he was able to prove a lot of things that other people had been unable to prove about Fourier series because he was willing to investigate infinity in this way. And it's really more of a completed infinity. Here's a quote from him. He says, "The fear of infinity is a form of myopia that destroys the possibility of seeing the actual infinite, even though in its highest form has created and sustains us. And in its secondary transfinite forms occurs all around us and even inhabits our minds." So you can see that he definitely thought of his study of infinity as being kind of connected to his views about God. That as he was studying infinity, he was kind of increasing his understanding of God's grandeur and who God is by studying infinity. And he wasn't afraid of it, right? A lot of people wanted to jettison completed infinity from mathematics, whereas Cantor really wanted to embrace it, or he was at least willing to embrace it whenever his mathematical researches led him in that direction. Cantor ended up proving all sorts of things about infinity. So one thing that he proved about infinity is that there's actually different sizes of infinity. Don't know if you've heard that, but not all infinities are created equal. Some infinities are bigger than other infinities. He was able to prove that the infinity of the real numbers, right, on the real line, is a larger kind of infinity than the infinity of the natural numbers, the counting numbers. That those two types of sets cannot be put in a one-to-one correspondence with each other. Not only that, he also showed that there is no largest size of a set. If you create a set, you can create a set that has a larger size, even when you're working with infinities. So the answer, if according to Cantor, can you do infinity plus 1? The answer is yes, and it's actually bigger than infinity, depending on what you mean by plus 1. But there is a next biggest infinity, or there is another largest infinity. So I didn't tell the young child that either. So, I restrained myself. Yeah. Again, I could do the proofs of some of these things, but that would take up probably the whole talk. I'm not going to do that. If you really want to know, take logic sets and proofs, or real analysis, or just come see me in my office. I'll talk to you. I'll prove it for you. Yeah, I'm always happy to talk about these things. It's pretty interesting. Now, there being a very long history of trying to get rid of infinity from mathematics, you can imagine there might be some backlash. Here's Leopold Kronecker. This is actually one of Cantor's teachers, but he was one of the harshest critics. Okay, that's kind of sad. So Leopold Kronecker really did not like Cantor's theories and felt that they were kind of a blight on mathematics and hoped that they would be eliminated from mathematics altogether. But the theory was being pretty successful because it was a pretty powerful theory. Kronecker said, something he said about infinity was, God created the integers, the finite counting numbers. All else is the work of man. Okay, that's said very disparagingly, like, okay, well, what's wrong with it being the work of man? But he means like you shouldn't study anything but just finite numbers. Everything else is just a fiction, an imagination. It's interesting how in both these quotes, they're connecting it to their theology somehow. Right? You're thinking it's hard, when you think about infinity, whether it's in mathematics or anything else, it's hard not to connect it back to what you think about God. Okay, well, so Leopold Kronecker was a opponent, but Cantor also had some defenders as well. Here's one of his defenders. This is David Hilbert. Super important guy in the history of mathematics, very influential. Kronecker was influential, but you can't get much more influential than David Hilbert. He was one of the leading mathematicians at the turn of the century, around 1900. And one thing that he said about Cantor's theories is he said, no one will expel us from the paradise that Cantor has created for us. It's pretty strong words. Is it really a paradise? I don't know. Some of the things that Cantor came up with it seemed pretty paradoxical. And he raised just as many questions as he solved. In fact, he might have even raised more questions. So for example, we know that the size of the counting numbers and the size of the real numbers, those don't have the same size, right? One's bigger. This is bigger than this. Is there anything in between those two sizes? Okay, that's a question that Cantor raised. Well, and he wasn't able to solve it. He kind of drove himself crazy trying to figure out how to solve it, but he was never able to solve it. It's called the continuum hypothesis. So there's a lot of weird things that happen. There's a lot of new questions that don't seem to be capable of being answered. Why did David Hilbert call it a paradise then? A lot of people wonder about it. Why did David Hilbert call it a paradise? Okay, so let's talk a bit about that. Why was Cantor's set theory, Cantor's theory of infinite sets, so powerful that David Hilbert would call it a paradise? One thing that I would like to mention at the beginning here is that infinite set theory is a way of unifying lots of different parts of mathematics into one theory. Have you heard about physicists looking for their ultimate theory, like the theory of everything? Have you heard about that? Physicists want to have a single theory that describes everything all at the same time. They don't want to have one theory that describes general relativity and another theory that describes quantum mechanics. They want to have one theory that describes everything. Well, the mathematicians are ahead of the physicists because we have ultimate theories. In fact, we have multiple ways of doing it. But the oldest one, and the one that is most common, is to think of everything as a set. Everything's a set. Everything in mathematics can be imagined as a set. And it's necessary that these sets be infinite. And you can use Cantor's theory of infinite sets to do that. So in one sense, it's a really powerful theory because it's kind of a mathematical theory of everything. You can describe it you can describe anything in terms of this theory that Cantor helped to create. But it's more than just that. It's more than just that. So to explain why it's more than just that, I do want to now try to get into the next part of the talk, which is about vector spaces. You do cover vector spaces in a course here. If you've taken linear algebra, you've talked about vector spaces. Sometimes that's not a very popular part of the class. But it's difficult because it's a new way of thinking. Right? It's very abstract. So vector spaces are things that behave like vectors. Okay? In mathematics, you sometimes do a lot of proofs or a lot of calculations, and you realize, I've done this before. I feel like I've done this a lot. Do I have to do this again? Have you ever felt that way? Well, you can sometimes realize that there are connections between all of these different types of problems and say, let me just call this, let me give a name to this phenomenon. Let me give a name to this so I don't have to reinvent the wheel every time I meet this problem. I can say, this is a vector space, therefore I know it's going to behave this way. Right? So vector spaces are things that behave the same way that normal vectors do. So if you've taken linear algebra, you've seen the list of what needs to be satisfied in order to behave like a vector. It's this list. There's 10 axioms. Okay? If you satisfy those 10 axioms, then you get counted. Right? You behave like a vector, and you're considered a vector space. This is Hermann Grassmann here, another mathematician. He's working pretty early. He was very ahead of his time in terms of his willingness to consider abstract structures like this. Now, something about vector spaces, maybe one of their most important properties is their dimension. So You can think of vectors, right? A one-dimensional vector, you can put it on a line. A two-dimensional vector, you can picture it on a plane. Three-dimensional vector, you can draw it in three-dimensional space. Four-dimensional vectors, we have a little harder time picturing that. Have you ever heard anybody say time is the fourth dimension? Right? So what are they? But that's not a spatial dimension, though, is it? Right? That's like, it's sort of like saying, okay, well, I'm going to meet you somewhere. Right? To really fully describe that, I need to tell you where I'm going to be in X, Y, Z space, but I also need to tell you the time I'm going to meet you. So it's an additional piece of information that's independent from the previous pieces of information that helps you know where I'm going to meet you. Right? There's four pieces of information. That's kind of what makes it four-dimensional. So if I start talking about infinite dimensional spaces, we might even have trouble figuring out four-dimensional spaces. But don't think of four-dimensional spaces as something creepy or weird. You got to think like a mathematician. And all the mathematician thinks when the mathematician is thinking about dimensions is how many independent pieces of information does it take to describe this thing that I'm talking about? So if I wanted to talk about, tell you X, Y, Z, and then a time, that would give you some information. But maybe at this particular place and in this particular time, there's this particular temperature. That's a fifth piece of information. Or it has this particular pressure. That's a sixth piece of information. If you plug that into a vector space, that's a six-dimensional vector space. Is this useful? Sure it is. There are lots of things in data science right now that you are a point in a very, very large dimensional vector space. They're trying to figure out, is this person going to want to buy the thing that I would like to sell them? Right? So they collect some information about you, independent pieces of information about you, like this and that and the other, all these different pieces of information. Like, okay, well you're a vector, a big vector that has all that information. It's all these different pieces of information about you. But typically they only can collect finitely. I don't think Google can collect infinitely much information on you yet. Only finite so far. So where does it? So I hope that this kind of gives you a picture of why mathematicians consider vector spaces, and also why they care. It's okay for the dimension to be large, right? If you're just thinking of dimension as being independent pieces of information. But where does the infinity come in? Okay. All right. Now I want to get back to Hilbert. Hilbert solved a lot of problems that had been left unsolved by Weierstrass. Remember, Weierstrass was the person who kind of put calculus back on its foundations by inventing all of our modern definitions of limits and continuity in terms of epsilons and deltas. He reproved rigorously most of the theorems of calculus, but there were some theorems he did not prove. He pointed out errors in other people's proofs, but he himself did not prove them, and that's not good. That's not good enough. You can point out errors in Riemann's proof, but you know if you're not going to prove it yourself, okay. Hilbert was able to solve some of those questions using, and he basically had to invent a whole new field to do it. Right? The field is now called functional analysis. Functional analysis because you're considering the vectors, the points in your space, to be functions. Okay. So we don't normally think like this, but with Cantor's set theory, it's very easy to start thinking like this. Everything is just a set. Right? Collect all the functions together. That's a set. How many dimensions are there? Well, is it a vector space? That's one thing. Okay. Can you add functions together? Can you multiply them by scalars? Is there a zero function? Are there inverse functions? You know, additive inverse functions? Okay, yes. Okay, so functions satisfy this definition, right? So is it a vector space? Yes. Well, then the next question, right? What dimension is it? Well, the thing about a vector is that there's finitely many coordinates, right? But a function, if I tell you what the function is doing at 0, and I tell you what it's doing at a half, and I tell you what it's doing at 1, okay, it's not necessarily a polynomial. It could be any function. If I tell you what it's doing at 0, if I tell you what it's doing at a half, I tell you what it's doing at 1, can you know what it's doing at 2? No, right? So if I specify like lots of coordinates of this function, is that going to help you figure out what the whole function is? No. To be a little bit more precise here, you have to think about in terms of a basis. Is there any a more rigorous way of saying this would be, is there any finite list of functions so that any other function could be expressed as a linear combination of that finite list? Okay, maybe that'll make sense to you if you've had linear algebra. Can you come up with a finite list of functions so that you can express all other functions in terms of those functions? The answer again is no. So function spaces, if you're considering the points, your vectors, to be functions, those are always infinite dimensional spaces because you can't determine them just by finitely many pieces of information. Well, Hilbert went to work on some of the problems that had been left unsolved. One of them was this one called the Dirichlet problem, right, which is a problem in differential equations. You want to find, given some continuous function on a boundary of a region, some other function defined inside the region that's a nice function, twice continuously differentiable, and it's harmonic on the interior, meaning that it satisfies Laplace's equation up there. So that's the Laplacian. If you've had Calc 3, you may not have seen that symbol in Calc 3, but it's really just the divergence of the gradient. Okay. So the divergence of the gradient equals 0. This is important in a lot of applied scenarios, solving this kind of problem, a Dirichlet problem, electrostatics, as we mentioned, and there's probably several others as well. It had not been shown that you could always find a solution. It had not been shown that you could always find a solution. Well, think about it with me. When you're trying to find a solution to a differential equation, you're trying to find a function that satisfies the equation, right? You're trying to, so your search space, the thing that you're trying to search through to see, can I find something that satisfies this, is an infinite dimensional vector space. So if you want to prove something like this, that you can always solve this, you might want to know something about the geometry of such spaces. Okay. And so, because David Hilbert had that ability to think about things in terms of these infinite dimensions, in terms of sets, okay, in terms of Cantor's theories, he was able to correctly approach this problem and end up proving it. And a lot of other things too. He developed what is sometimes called Hilbert space. If you've had Calculus 3, you've seen the dot product, right? You do, in that top line there, you just take all the coordinates of the vector, multiply them together coordinate-wise, and then add them all up. Okay. Well, what if you have infinitely many coordinates, like a function does? How do you sum up infinitely many things? You integrate, right? Can you see the similarity between that formula on the bottom there and that formula on the top? I mean, you're just multiplying all of the coordinates together and then summing them up. An integral is a continuous sum. Okay. So the way that a dot product works in finite dimensions, this type of inner product works in infinite dimensions. Similar with the norm, right? So how do you measure the magnitude of a vector? Right? You sum up the squares and then take the square root. I can do that with an integral too, right? If there's infinitely many coordinates, I can square them, integrate them, take the square root. So this has proved to be a very useful way of thinking about function spaces as well. It's been used in quantum mechanics and many other places also. And so he actually spent David Hilbert worked in a lot of different fields. Some people consider him to be kind of the last mathematician that worked in all fields, although I hear that Poincaré also has a claim on that title. But whether it's Poincaré or Hilbert, they both tended to work in lots of different fields. Hilbert spent about 10 years working on these types of problems and solving a lot of things that had been up until that point unsolved from this perspective. Okay, now I want to just a little bit talk about Banach spaces, because this is actually what I study. So Stefan Banach was another mathematician. Let me tell you a little bit about him. He has a very interesting life. He started from pretty humble beginnings. There's a picture of him. Everybody say, "Oh, that's a pretty cute picture, isn't it?" That's a pretty cute picture. So his mother died when he was very young. I don't remember if it was in childbirth or it was just whenever he was very young. his father kind of disowned him and sent him to live with other people, and he never really knew his father. So pretty humble origins. But he was very gifted in mathematics. He showed promise from a very early age and was primarily self-taught. So there he is as a young man, being very studious. Looks like he could be out there as one of you. I feel like I've seen him around here somewhere, or somebody who looks like that around here somewhere. Okay, so that's Banach studying as a young man. He learned a lot of mathematics independently. One day, he was explaining the Lebesgue integral to another person in the park, and a famous mathematician walked by him and overheard him talking about the Lebesgue integral. Okay, if I was walking through a park and I saw somebody on a bench talking about the Lebesgue integral, I would stop and talk with them also. Like, oh, you too? So that's what happened to him, and there's now like a statue in the place where this happened that commemorates this. So Steinhaus is the person who discovered Banach and was walking past and said, oh, this person knows a lot of math. I need to get acquainted with this person. And Steinhaus later said that discovering Banach was the most important mathematical discovery that he made. So Banach actually, so he connects him with the larger mathematical community and gets to know all of the famous mathematicians. He kind of starts this school and it brings a lot of people in to his circle of influence, and they start doing mathematics together, called the Wolf School of Mathematics. And they often would meet in this place called the Scottish Cafe. I think named maybe for the architecture, maybe for the food, but this is in Poland. Okay, this is a Polish mathematician. Now it's in Ukraine, actually. Those borders change a lot over there. Okay, so it's in Ukraine now. But it was part of Poland at the time. They would meet at this Scottish cafe, and there was like a marble table, and they would all like do their calculations on this marble table, and it just in pencil, and then somebody would have to come and wash it, and eventually somebody bought him a book, right, to like write your things down in this book, and so it became a very famous book. It's called the Scottish Book. Okay? It has a list of very important mathematical problems that remained unsolved for a very long time. Many of them. They would sometimes, they were good spirited about this. They would list these problems and they would offer prizes for them. Some of the prizes were like, okay, you get this nice pen, or you get this bottle of brandy. One of the really big ones was you get a goose. Okay, I'll give you if you solve this problem, I'll give you a goose. That's nice. Banach's story kind of has a sad ending. All this is happening and leading up to World War II. Okay, then Nazis. Okay, they were fun. A lot of the people in Banach's circle were killed. Some were put in concentration camps. Some committed suicide to avoid being captured. Banach himself, actually, they gave him an option. He could go to a concentration camp, or he could become a feeder of lice. What's that? It doesn't sound good, does it? Okay, well, a feeder of lice is someone that they would use, they would strap lice to you, and in this process that they would use to make a vaccine for typhus. Okay, so he chose to do that. I guess maybe better than concentration camp, but still not very pretty. He died a few years after Poland was emancipated. Not from typhus, fortunately, but he actually died from lung cancer. He was a heavy smoker. But yeah, so his school has a very sad ending. But the problems themselves, through this book, lived on. Right? The problems themselves lived on. I'm running a bit out of time, so I don't know how well I can explain what some of these problems are. But they have to do not with Hilbert spaces, but with Banach spaces. That's what I studied. There are other infinite dimensional vector spaces, but they're ones that you still feel like you should be able to understand. Hilbert spaces actually nowadays are pretty well understood. Not everything's understood. They're still hard, right? There's still unsolved problems. But most things, it's well understood. Banach spaces are kind of the next thing you would consider. They don't necessarily have an inner product, but they do have a norm. They don't necessarily have an inner product, but they do have a norm. No one would ever try to classify all possible infinite dimensional topological vector spaces. No mathematician is crazy enough to try to mathematicians were trying to completely classify Banach spaces. He didn't call them Banach spaces, by the way, just in case you're wondering. He called them spaces of type B. Pretty smart idea. If I invent a space, I'm going to call it a space of type K. So here's an example of a problem that was in the book. Does every separable Banach space have a Schauder basis? You have to decide what you mean by basis in this context. It means this. Okay. You want a sequence of vectors so that for any other vector in the space, you can express it uniquely as this. Okay, now remember, these are infinite dimensional vectors. This is an infinite series. You have to worry about convergence, and convergence is a lot harder than in calculus 2 because you're talking about things in infinite dimension. But it's the same kind of thing. And maybe you don't have the ratio test, but there's other stuff. Okay, so this was a big question. You feel like there should always be a basis. In a Hilbert space, you can always find an orthonormal basis if the space is separable. In a Banach space, you might not be able to do that, but who knows? You know, it's a question, open question. The answer ended up being no. This wasn't solved until the 70s. There's a lot of really, really deep questions in Banach space theory, and you need to use Cantor's theory of infinite sets to be able to talk about these questions. So the person who solved this in the 70s, what happened? Was there anybody left alive to give the goose? Yes! Yay! All right, good. There were some people left from the original circle that were able to give the goose, right? So it took 30 years to eventually do that. Okay. So I'm not going to be able to talk. I'm happy during lunch, if you'd like to come, I'm happy to talk about the types of questions that I consider. But let me just mention that, so the line goes from Stefan Banach to Stanislaw Mazur, Alexander Pelchinsky, Nicole Tomczak-Jagerman, then my advisor, Bumi Ansari, and then me. Okay. So, I chose to publish my first article actually in the journal that Banach founded in Poland called Studia Mathematica that he founded with his circle at the Scottish Cafe. So I am definitely in the line of studying these types of questions and still very interested in them and trying to understand why these spaces work the way they do. All right, that's my talk.
Thank you. Now we'll have to go to the corner cafe and write our questions on the table there. And we'll get answers to them in the years to come. Given the hour, let's just thank Dr. Krause again, and we'll all meet up again at the choice room in the corner cafe if you want to come join us for lunch. If you don't have a meal plan, come see me, and I can buy you your lunch. Yes? Otherwise, let's thank Dr.
Okay.